Hello, and welcome to the University of Kentucky Anesthesia YouTube channel. My name is John Green. I'm a pediatric anesthesiologist, and I'm one of the associate program directors here at our residency program. Today's presentation is a continuation of our keyword review series for the basic exam content. In today's presentation, we're going to be going over vaporizers, as well as uptake and distribution of anesthetic gases. We'll start with vaporizers. So first we need to review a few gas laws. The ideal gas law states that the pressure of a gas times the volume that confines that gas is equal to the number of molecules of the gas in moles times R, which is the universal gas constant, times temperature in degrees Kelvin. So what this tells us is that the pressure of a gas is directly proportional to the number of molecules of gas and also to temperature, and that the pressure of a gas is inversely proportional to the volume that contains that gas. The next law is Dalton's law of partial pressure, which states that in a mixture of gases, each gas creates a partial pressure equal to the same pressure as if it occupied that container by itself. And the total pressure of the system is the sum of each partial pressure of each gas. Now, combining the ideal gas law with Dalton's law of partial pressure, we see that the partial pressure of a gas A is equal to the total pressure of the mixture times either the mole fraction, which is that N sub A divided by N subtotal, or times the volume percent of the gas, which is that V divided by V percent. So vapor pressure is another concept that we need to look at. Volatile liquids have a high propensity to enter into the gas phase or vaporize. And there are two things that occur: evaporation and condensation. Evaporation occurs when molecules at the surface of the liquid have enough kinetic energy to escape and enter the gas phase. Now, it's important to understand that evaporation is a surface phenomenon. It only happens at the surface of the liquid, as opposed to boiling, which happens throughout the liquid. Condensation occurs when those molecules in the gas phase return back to the liquid phase. And so if you have a liquid volatile anesthetic in a contained space, you have evaporation and condensation occurring simultaneously, and eventually an equilibrium will be reached at which that gas phase above the liquid is saturated and creates a partial pressure known as the saturated vapor pressure. Vapor pressure is directly proportional to temperature, in that as temperature increases, a liquid's vapor pressure will also increase. You can see that this is a curve rather than a linear relationship, and that curve is intrinsic to each individual liquid. So, for instance, Desflurane is here. It has a much higher and more rapid temperature curve compared to, say, Sevoflurane, which is down here. It's also important to understand that vapor pressure is independent of atmospheric pressure. Now, there are some concepts that we need to discuss that are related to vaporizer design. The first of these is latent heat of vaporization, in which evaporation requires energy in the form of heat, which is absorbed from the surroundings. In a container, this energy primarily comes from the liquid itself. So as that energy is absorbed from the liquid, it causes that liquid to cool, which results in a subsequent reduction in vapor pressure. Most vaporizers have a temperature compensation mechanism to combat this. Specific heat is defined as the number of calories required to increase the temperature of 1 gram of substance by 1 degree Celsius. It indicates how much heat must be supplied to the liquid in order to maintain a constant temperature due to the latent heat of vaporization. So vaporizer materials have a high specific heat in order to minimize temperature changes. Thermal conductivity measures the speed with which heat flows through a substance, and vaporizers are constructed of metals with a high thermal conductivity in order to maintain uniform internal temperature. And then boiling point is the last concept. We already discussed that boiling basically is evaporation that occurs throughout the liquid. This leads to rapid, uncontrolled vaporization. Now, it doesn't really come into play with most volatile anesthetics because most of the volatile anesthetics have boiling points from 48 degrees Celsius to 59 degrees Celsius, and the operating room environment will never get that high. The difference is with Desflurane, which has a boiling point of 22.8 degrees, which is very close to room temperature. So if the operating room is at or above room temperature, it could cause boiling with Desflurane. So Desflurane vaporizer has a special design. So now that we've talked about some of the concepts related to vaporizers, we'll go over the vaporizer types. And there's two ways to describe vaporizers. The first is in relationship to the circuit. Either out of the circuit or in the circuit. Most of our modern vaporizers are out of circuit, but in-circuit vaporizers are still seen mainly in resource-constrained environments and in the intensive care units. As to the specific types, you have variable bypass, dual circuit, cassette, and injection. The first type we will discuss is the variable bypass vaporizer. So the saturated vapor pressure of volatile anesthetics far exceeds the clinically useful concentrations. So that vapor pressure must be diluted to a safe and clinically relevant range. The variable bypass vaporizer accomplishes this by diverting or splitting the carrier gas. So you can see gas will enter over here, and then the vast majority of that carrier gas will flow through this bypass chamber and never combine with the anesthetic gas until the very end. But a portion of that carrier gas is diverted down here into the vaporizing chamber, where it basically comes in and picks up anesthetic gas molecules from the saturated vapor pressure, and then it comes back up to combine with that carrier gas to the output. The concentration control dial determines the ratio of gas that flows through the bypass chamber and the vaporizing chamber. And then a temperature compensating device further adjusts that ratio. The vaporizer concentration control dials are labeled to set vaporizer output in terms of volume percent and are calibrated at sea level. Now, the specific ratio of fresh gas flow divided between the bypass chamber and the vaporizing chamber is known as the splitting ratio. Different concentrations result in different splitting ratios. And the physical properties and clinical concentrations of each agent are unique. So the splitting ratios are specific to each agent and dial setting. Thus, vaporizers are agent specific. So in this diagram, you can see that this is specific to sevoflurane, and at a 2% concentration dial, it has a ratio of 12:1, a split ratio. As that concentration dial is increased or decreased, it changes that split ratio. Now, the other thing to notice about this is the inflow, the carrier gas, is coming in at 2,000 milliliters per minute in this particular scenario, but the output is higher. It's actually 2,040 milliliters per minute. And that's because it's actually picking up additional anesthetic gas down here. So the take home is that the outflow actually is going to be higher than the inflow. Remember that temperature affects the saturated vapor pressure. So a temperature compensation mechanism further alters the ratio of gas flowing through the bypass and vaporizing chambers. At lower temperature, the saturated vapor pressure of the liquid anesthetic decreases. This results in less gas molecules to pick up in the vaporizing chamber. Thus, more gas is diverted to this chamber in order to pick up the same goal number of gas molecules. The opposite occurs as temperature increases. Mechanisms can be either a bimetallic strip, which is seen on the left here, that basically adjusts its position in relation to the temperature, or an expansion-contraction element, which is this cone-type design on the right. Now, there are factors that can further influence the output of variable bypass vaporizers. The first of these is extremes of fresh gas flow, most notably very low rates, such as less than 250 milliliters per minute, or very high rates, such as 15 liters per minute. At very low rates, it will be less than the dial setting due to an insufficient turbulence in the vaporizing chamber. And at very high rates, it will be less than the dial setting due to rapid evaporation, incomplete mixing, and failure to fully saturate the carrier gas in the vaporizing chamber. The temperature compensating mechanism affects a linear change, which does not precisely match the vapor pressure curve. And if you remember, those are the vapor pressure and temperature is an actual curve rather than a linear relationship. Intermittent back pressure can occur from either positive pressure ventilation or oxygen flush valve use, which basically is a retrograde transmission of pressure when the patient circuit compresses gases in the vaporizer, and then when that pressure is suddenly released, vapor can exit through both the outlet and retrograde through the inlet, all of which may lead to a higher than expected vaporizer output. The carrier gas composition can affect the output, most notably with nitrous oxide, which is more soluble than oxygen. And so when it passes through the vaporizing chamber, that nitrous oxide can readily dissolve in the liquid, which can decrease the output of the anesthetic gas. And then barometric pressure changes can also affect the output. Now, barometric pressure changes, or the ambient pressure, can significantly affect the volume percent output, but the effect on partial pressure is minimal. Remember that it's not volume percent, but partial pressure that is of the gas that is most important. And while the volume percent may change on the output, when it combines with that atmospheric pressure, it has relatively little effect of change on the partial pressure of that agent. The only exception to this is with the Desflurane vaporizer, which we will soon discuss. Now, there are some safety mechanisms that are inherent to the variable bypass vaporizers, such as they are agent-specific and have keyed filling devices which prevent filling with the incorrect agent. The filler port is located at the maximum safe liquid level in order to prevent overfilling. Vaporizers themselves are firmly secured to the manifold on the anesthesia workstation to prevent tipping. And then there's an interlock system that prevents the administration or the use of two vaporizers at once. You can only use one vaporizer at a time. Desflurane has some differences that preclude its use with contemporary variable bypass vaporizer. Most notably, its high volatility and its moderate potency. So the high volatility would cause a high rate of evaporation. This would require excessive diluting gas and also excessive cooling of the anesthetic liquid. And we also mentioned that the boiling point of Desflurane is very close to room temperature. And if boiling occurs, the output would be uncontrollable. So the Desflurane vaporizer design is a little bit different. It electronically heats to the liquid to maintain a constant temperature and vapor pressure. And it is a dual circuit vaporizer in which the carrier gas is not split. The Desflurane vaporizer is a dual circuit vaporizer that provides two independent gas circuits arranged in parallel. The Desflurane reservoir is heated to 39 degrees Celsius, which provides a consistent saturated vapor pressure. The output is controlled by the concentration control valve, which controls that R2 variable restrictor. And then finally, there is a differential pressure transducer. What it does is it allows for the vapor circuit pressure to match the fresh gas circuit pressure. And this allows for same dialed concentration regardless of the flow rate. There are factors that can also influence the output for the Desflurane vaporizer. The first that we'll discuss is barometric pressure changes. Remember that with the variable bypass, barometric pressure changes will change the volume percent output, but it in effect does not change the partial pressure very much. Well, with Desflurane vaporizer, it maintains a constant volume percent. So if your ambient pressure changes, it will definitely affect the partial pressure. For instance, at high altitudes, which is a lower atmospheric pressure, the partial pressure of Desflurane will actually decrease. So the concentration output must be increased in order to deliver the same partial pressure that you would at sea level. The carrier gas composition can also affect the output, most notably again with nitrous oxide, but this is due to the lower viscosity than oxygen. That lower viscosity can cause less pressure in the fresh gas flow circuit from that R1 restrictor, which can transduce a lower pressure to the vaporizer circuit, which may lower the vaporizer output. Desflurane vaporizer also has some inherent safety mechanisms. The system design prevents filling with incorrect agent, and it also prevents leakage. And then it also has a shutoff valve that will close with some major faults, which include an anesthetic level decreasing below the threshold, tilting of the vaporizer, a power failure, or an excessively high pressure difference between the vapor and fresh gas circuit. The Cassette vaporizer operates like an electronic, computer-controlled variable bypass vaporizer. There's an internal control unit that's housed within the anesthesia workstation, and this interacts with interchangeable cassettes that are color-coded and magnetically coded to each individual agent. In the cassette, the agent freely vaporizes to saturated vapor pressure, and a CPU modulates a flow control valve, which precisely regulates the amount of gas flowing through the vaporizing chamber to join with the bypass flow. That CPU receives input from multiple sources, including a concentration control dial, pressure and temperature sensors inside the vaporizing chamber, and flow sensors in the bypass and vaporizing chambers. Since the cassette is electronically controlled, Desflurane can be used. And additionally, if the room's temperature exceeds Desflurane's boiling point, then the cassette will convert to function as a vapor injector, which we will talk about soon. Safety mechanisms of the cassette vaporizer include protecting from a hypoxic gas mixture less than 25% oxygen, a check valve that prevents the liquid from entering the fresh gas line. If the cassette is removed, valves close, and that prevents a loss of the fresh gas. And then the design of the cassette is immune to tipping, so it has no restrictions on orientation during handling or storage. With the injection vaporizer, gas from an anesthesia machine enters through the drive gas inlet and pressurizes the liquid anesthetic reservoir. This provides enough force to inject liquid through an injector where it enters a heated vaporizing chamber and leads to rapid evaporation and allows for combining that anesthetic gas with the fresh gas. There's no concentration control dial. Instead, there's an electronic microprocessor that's adjusted via the workstation interface, and this controls the amount of liquid that's injected into that chamber. A dedicated gas analysis line downstream from the vaporizer monitors the output, and injection vaporizers are also agent-specific. Some of the safety mechanisms inherent with the injection vaporizers include a safety valve that stops the flow of agent if the vaporizer malfunctions. It is also not vulnerable to tipping, and then there are alarms when the anesthetic level falls below a certain threshold. Now, when talking about in-circuit vaporizers, there are two main designs. On the left, you'll see the Oxford miniature vaporizer, which is useful in limited resource environments, such as areas where they don't have commercial anesthesia workstations available. It functions very similarly to a variable bypass vaporizer. There is a calibrated dial that controls the flow through an aperture between the slide valve and the obturator and the bypass chamber, which diverts flow to the vaporizing chamber. There are metal mesh wicks that increase the surface area for vaporization. There's no temperature compensation mechanism, but there is a heat sink of water and ethylene glycol that's housed in the base to help resist temperature swings. It is not agent specific, but there are different calibrated dials that are available for each agent. Now, volatile anesthetic reflectors, they are useful in the ICU setting, and they're based on the same design as the heat and moisture exchanger filter. There's liquid anesthetic that is injected into the device, and vaporization occurs through this evaporator rod. And then there's a carbon filter that absorbs the anesthetic with exhalation, and that allows for, quote, reflected rebreathing with inspiration. We'll now switch gears and talk about the uptake and distribution of anesthetic gases. So here is a diagram that just shows a general overview of the delivery of the anesthetic agent. Fresh gas flows go through the vaporizer. It picks up anesthetic, which is delivered into the ventilator circuit. The patient breathes in that gas to the ventilator circuit. That anesthetic agent goes down to the alveoli, where it crosses into the pulmonary blood flow and is delivered to different tissues. You can see there's three main ones that we talk about, which we'll go into detail here soon. And then that anesthetic gas goes back into the venous blood flow, comes back to the pulmonary circulation, where it either picks up more anesthetic gas or delivers the anesthetic gas back to the alveoli, where it's exhaled. There are some important concepts to review before talking about uptake and distribution. We have the fractional concentration of alveolar anesthetic, which is designated by F sub A. You have the fractional concentration of inspired anesthetic, that is the anesthetic leaving the anesthesia circuit, and that is designated by F sub I. We also have the partial pressure of anesthetic in the alveoli, the partial pressure of anesthetic in the blood, and partial pressure of anesthetic in the central nervous system. On the right, we see that the fractional concentration of alveolar anesthetic is equal to the partial pressure of anesthetic in the alveoli divided by the barometric partial pressure. This tells us that fractional concentration of alveolar anesthetic is directly proportional with the partial pressure of anesthetic in the alveoli. This is useful when assessing uptake, which we will soon see. And the partial pressure of anesthetic in the alveoli is an important factor when considering uptake and distribution because it is in rapid equilibrium with the circulating blood and highly perfused tissues, including the CNS. And it can also be measured in exhaled end-tidal gases. Thus, the partial pressure of anesthetic in the alveoli in the exhaled breath represents a useful estimate of the partial pressure of anesthetic in the central nervous system. And remember that the partial pressure of anesthetic in the CNS is the main determinant of anesthetic level. Anesthetic flows from the alveolar gas to pulmonary blood across the alveolar capillary membrane, and this is driven by the partial pressure gradient between the alveolar gas and mixed venous blood. The reverse occurs with washout during emergence. Now recall that the fractional concentration of anesthetic in the alveoli is directly proportional to the partial pressure of anesthetic in the alveoli. So the rate of rise of FA to FI is a good way to assess anesthetic uptake. It reflects the speed at which alveolar anesthetic equilibrates with that being delivered to the lungs. In essence, the faster the rate of rise, the faster the speed of induction. Now, the rate of rise of FA to FI is primarily dependent on anesthetic solubility in the blood, cardiac output, and alveolar ventilation. The anesthetic solubility in the blood is inversely related to the rate of rise of FA to FI. The way to think about this is if the anesthetic is not very soluble in blood, less of that anesthetic is going to be transferred to the pulmonary circulation, so the rate of rise of FA will increase. Cardiac output is also inversely related. The way to think about this, in a lower cardiac output state, you have less blood being delivered to the lungs, thus less anesthetic is going to be delivered from the alveoli to the pulmonary circulation, also increasing the rate of rise of FA. And alveolar ventilation is directly proportional to the rate of rise of FA to FI. This makes sense because you have more anesthetic being delivered to the alveoli. That's going to increase the rate of rise. To further discuss the anesthetic blood gas solubility effect, at a given inspired concentration of anesthetic, cardiac output, and minute ventilation, the maximum FA to FI is highly dependent on the blood gas partition coefficient. You can see on the graph on the left the relatively insoluble anesthetic gases such as desflurane and nitrous oxide. The rate of rise is much faster than that of sevoflurane and isoflurane. The graph on the right shows the blood gas partition coefficients of each agent. Now it is noticeable, you may notice that desflurane has the lowest blood gas partition coefficient, yet nitrous is actually a faster rate of rise of FA to FI. This is due to the concentration effect, which we will discuss in a little bit, and the fact that nitrous is typically given at 50 to 75%, whereas Desflurane is typically given at around 6%. So while Desflurane has a lower blood gas partition coefficient than nitrous, because nitrous is such a high percentage usually, its rate of rise is faster than Desflurane. Additional factors that can affect uptake of anesthetic into the pulmonary system include pulmonary dead space, which reduces effective alveolar ventilation. So less anesthetic is delivered to the alveoli. This decreases the rate of rise of FA to FI. And it's more pronounced with high fresh gas flows and low blood solubility agents. Pulmonary shunting bypasses alveolar uptake, so less anesthetic is removed from the pulmonary gases, which increases the rate of rise of FA to FI, and it's more pronounced with low blood solubility agents. Concentration effect, we mentioned earlier, this is when an anesthetic represents a very large fraction of the inhaled gas mixture, such as nitrous oxide. And its rapid uptake results in a smaller relative alveolar anesthetic concentration drop because the volume of the alveolar gas also decreases. And then second gas effect is a similar effect in which, so in the previous example, after uptake of that large portion of nitrous oxide, the relative partial pressures of oxygen and volatile anesthetic increase due to the relatively lower volume, as well as the subsequent replacement with fresh gases. After the uptake of anesthetic gas into the pulmonary circulation, that gas is distributed to various tissues throughout the body. You can see the first one we'll talk about is the vessel-rich group, which is the heart, brain, lungs, spinal cord, liver, and kidney. It comprises about 10% of the body mass, but it has 70% of the cardiac output. The next one is skeletal muscle, which represents about 40% of the body mass, and it receives about 10 to 15% of the cardiac output at rest. Fat comprises about 25% of body mass, and it receives about 10% of cardiac output. And then the vessel poor group includes skin, bone, and connective tissue. It accounts for about 10 to 15% of body mass, but it only gets less than 5% of cardiac output. While technically there are 4 tissue groups, we traditionally think of 3 main groups of tissue for anesthetic distribution. That's the vessel-rich group, the skeletal muscle group, and the fat group. The rate of distribution of anesthetic into each tissue is determined by the tissue-specific blood flow, or the cardiac output, the effective volume of the tissue, which is a product of both the anatomic volume and the tissue's blood solubility of the anesthetic agent, and the anesthetic partial pressure gradient between arterial blood and the tissue. When looking at the rate of equilibration, the anesthetic equilibrates in the vessel-rich group quickest, followed by skeletal muscle, and then finally fat. Now, the vessel-rich group equilibrates the quickest due to relatively small effective volume and the greatly increased blood flow. As far as muscle and fat, they have similar cardiac output, but despite having a higher body mass percentage, muscle equilibrates faster than fat, and this is primarily due to fat's much higher effective volume, which is a result of the high fat blood solubilities of anesthetics that you can see in the graph to the right. In fact, although fat has the largest effective volume, equilibration is so slow that this compartment usually plays a relatively minor role in the pharmacokinetics of inhaled anesthetics, unless we're talking about very long anesthetics. During a typical general anesthetic lasting less than about 4 hours, the blood, the vessel-rich group organs, and the muscles are the compartments into which inhaled anesthetics mostly distribute. Finally, a note about nitrous oxide. Nitrous oxide is the exception, as you can see that the partition coefficients are fairly similar in each tissue. Nitrous oxide doesn't really accumulate to any great extent, and it's not a very potent anesthetic. Its utility lies mainly as an adjunct to potent agents and as a vehicle to speed induction. This concludes the presentation. Here is a list of my references. Thank you for listening.